The first example we're going to look at is available in my GitHub repository in the Java 8 EX16 folder in my live lessons repo. So if you go to my GitHub repository and you look under live lessons in the Java 8 EX16 folder, you'll find the example that we're about to walk through here. So here's the code we're going to look at first in my IntelliJ project. This program implements various ways of computing factorials using BigIntegers, which means we can have essentially arbitrary precision factorials. And we're using this for a couple of reasons. We're using this to showcase the performance of different alternative parallel and sequential algorithms using different frameworks in Java and reactive programming, including Java sequential and parallel streams, as well as sequential and parallel reactive streams implementations using RxJava and Project Reactor. This particular example is also kind of fun because it demonstrates the dangers of sharing unsynchronized state between threads, which is always an issue that you run into when you start trying to write code that runs efficiently on multi-core processors. You can get yourself into some trouble. And we'll kind of talk about sort of the conventional way of doing things, and then we'll talk about different approaches here. So we're going to basically do 20,000 iterations, and we're going to compute the factorial for 1,000, which, as you can imagine, is a very, very large number. I'm going to go ahead and start this thing running in the background. It takes a little while to run, so we'll come back and look at it when we're done looking at the code. So the first thing we're going to do is we're going to warm up the fork join pool just so that the timing should be as accurate as we can make them by warming up the pool. That there should be threads that are already spawned when the examples start to run. The fork join pool that comes with Java will essentially do the allocation of the threads lazily when the thread pool is first accessed. So we don't want to penalize the first use of the thread pool relative to other uses. And then we're going to run a whole bunch of different tests. We have a very simple sequential factorial, which just does the classic way using a for loop. We have a sequential streams factorial. We have a couple of factorials that use RxJava and Reactor observables and fluxes, respectively. Then we start migrating to parallel processing. And as you can see here, we have a somewhat whimsically named buggy factorial, which shows how not to do parallel processing. And then we've got a bunch of different parallel implementations that use parallel streams, a couple different parallel streams implementations, one that uses something that's called RxJava parallel flowables. And then we're also going to use Project Reactor's parallel fluxes. And then finally, just to kind of round everything out, we're going to use a version of the buggy factorial that puts an explicit synchronized statement in to protect the integrity of the values that are being accessed and updated concurrently. And we'll see that that one works correctly, but it is really slow. When we're all done, we print the results and we're done with the tests. Let's see what happens when we ran everything. As you can see here, we're computing the factorial for 1,000. And most of these values have the same results, except for buggy factorial. And the buggy factorial, of course, has a different result because it's buggy. So even though it's very efficient, it's very broken. And so it's a great example of not wanting to optimize for performance before you get correctness working properly. Here are the results. We'll talk about these things more in more detail later. You can see that there's a bunch of things that are pretty similar. The Reactor, Project Reactor parallel flux is the fastest version, followed by parallel streams, followed by RxJava parallel flowables. They're all roughly about the same performance. Then you can see the sequential versions are slower. The sequential version that does not use streams or reactive programming at all works ever so slightly faster than the versions that use those higher level frameworks. That's not unusual. We expect that. There's a little overhead for using abstraction, of course. But notice how much faster the parallel versions of these things work relative to the sequential versions, demonstrating that abstraction can actually be a big performance win. And then finally, down here at the very bottom, the synchronized parallel implementation that we'll look at here shortly performs the worst, and it's about 6 times slower than the other versions. And one reason for that is it's heavily serializing access to a common mutable variable, whereas the versions that use parallel streams and parallel fluxes and parallel flowables and so on are not serializing. So they're able to take better advantage of all the cores that we have available on this particular platform. This particular machine I'm running on has 10 hyper-threaded cores. It's running the M1 Max Apple chip. So it's pretty darn fast. You can see that there's some real benefits to the speedups you get here. So with that as background, let's go ahead and take a look at the tests. First of all, you'll see that all these tests are all being called via a common run test harness. And this is kind of cool. So I'm going to show you how this works. You can see that we pass in the string that's going to be used for the diagnosis, the diagnostic information. We pass in a method reference to the particular function we want to have run to compute factorial, and we pass in n, which turns out to be 1,000 in this case. Here's the run test method. You can see it's pretty cool. It takes a function, that's the function to run, that's the factorial method to run. And then it uses the garbage collector it basically goes ahead and runs the garbage collector so that we collect all the garbage before we start doing any timing. We then have a call to this time run method, which is a little helper method that I've written that goes ahead and keeps track of the starting time, runs the particular method or the particular runnable that's passed to it, then stops the time and then puts the test name into a map with its execution time so we can get the results later. So what we're about to do is time the computations. What we're going to do here is we're going to run this thing for 20,000 iterations, calling the apply method on the factorial function that's passed in, which will compute the factorial with whatever algorithm we pass in. And when we're all done, we go ahead and print the results out. So this is kind of cool because it makes it possible to test the results in a very apples to apples way. So with that out of the way, let's go ahead and take a look at the different implementations, starting with the real simple one. This is just meant to be a baseline using a classic sequential algorithm to compute factorial. You can see here it takes a big integer, makes a local variable that's going to start with a value of 1. And we basically iterate through a loop using good old for loop. And we multiply f, which is the local variable, by the value of I, which is loop counter, turning it into a big integer. So we take f and we multiply it successively by 2, 3, 4, 5, 6, 7, et cetera, until we're done. And then we return the result. So that's kind of the classic way of doing things. If you've ever written a factorial program, you've probably done something like that. Now let's go ahead and take a look at the sequential stream implementation, which, as you saw, was within striking distance of being as fast as the good old for loop. What this does is it uses something that's called a long stream, and we generate a range of values for 1 up to the long value version of n. And then we go ahead and we convert those longs into big integers. And then we use what's called a terminal operation with Java streams to go ahead and multiply pairwise each of the integers in sort of a tree-like manner until we're going to end up with a final result, which is the factorial. So this is what's called a reduction. Reduce is a very common type of method or an operation in functional programming, and we use it to basically reduce that stream of big integers to a final single result, which is initialized with the value of 1. Okay, nothing too surprising then. Here we have another implementation. This uses RxJava. You can see that the RxJava implementation looks very, very similar to the streams implementation. The main difference is that RxJava by default wants to return these things called observables. And therefore, if we don't want to have to do an asynchronous type of program, which we do not in this case, we're going to have to block at the end of this thing. So we compute a range of values from 1 to n. We turn them into big integers. We multiply them using reduce to get a single reduced result. And then we say, please block until all that computation is done. When we get a little further along, we'll look at ways to avoid having to do this blocking call. But for this simple program, we're going to do it that way. Here's the way you do the same thing with the Project Reactor Flux instead of an observable. You can see it's very similar. but instead of saying observable, we say Flux. And otherwise, it looks all the same, except that there's a method called block instead of blocking get. Okay, those are the simple ones. Nothing particularly profound there, just kind of showing you a baseline to diverge from as we start using the more interesting parallel implementations. But before we do that, let's take a look at what not to do. And what you don't want to do is you don't want to have mutable shared state that will be corrupted by multiple threads accessing it and updating it concurrently without proper synchronization. So to demonstrate this, we have another example called buggy factorial. And we have a little nested class here called total. And total has a field called mtotal, which is just the local field, that starts out with a value of 1, big integer value of 1. And it's also got a multiply method that takes an integer and it updates mtotal by multiplying itself by n and then storing the results into mtotal. So far, so good, right? That looks reasonable. But let's see what happens when we fail to follow the edict to avoid shared mutable state. Shared mutable state is the root of all evil in concurrent programs, and we certainly don't want to do things like we're going to show here. So here we go ahead and make ourselves a local variable of new total. We iterate through our stream from 1 to n. We run everything in parallel. Now we're using Java parallel streams. Notice we just have to put one little dot parallel call here, and all of a sudden it's a parallel stream. And that means that these computations are going to be mapped to different threads in the common fork join pool, which is a pool of threads that comes out of the box with Java parallel streams and also with completable futures. We turn it into a big integer, and then here's where things go awry. We're going to use the for each method, it's a terminal operator, to multiply all the values in parallel. But the problem is that we're doing the multiply on this single instance of a class total, which has a shared mutable object. You can see here it's being modified by the multiply method, but you'll notice that there's no synchronization. So it will incur race conditions. I should say will incur race conditions when run on a multi-core computer or processor. And of course, it's pretty darn hard not to have a multi-core processor these days, so this will incur race conditions because this value is being updated by multiple threads simultaneously through this call to multiply. So that's problem number 1. And as you saw, the results that came back were nonsensical. And then we're also returning the total here, which isn't properly synchronized, so that can cause problems too. So the long and the short of it is, don't write code like this. Instead, use the features that we're going to talk about to get support for functional and or reactive parallelism in order to be able to speed things up, write super clean code, and never have to worry about race conditions again. So we'll take a look first at a very simple example. This is a version of a synchronized parallel factorial implementation that uses Java parallel streams. And you can see here what this is going to do. Oh, I take it back. This is not using parallel streams. This is using just good old synchronization. So this approach is just almost identical to the code we saw before up here in buggy factorial. The difference being that we're going to use a synchronized statement here when we do the multiply. So every call to the multiply method will be properly synchronized. There's also a get method that we use to return the value. Otherwise, the code looks pretty much identical for the most part. It has a parallel stream, it calls map to object, it calls for each, but this time everything's synchronized properly. The problem, however, is even though we get the right result, we get the result we expect, this solution is really slow. And that's because we are serializing access to that shared mutable object. And so all those threads, even though we've got a whole bunch of threads running around in our pool, they're all having to serialize their access here in the multiply method. So we're really not getting much of a bang for our parallel computing multi-core processing buck, which is a problem. So let's see how to fix those things. Let's take a look first at the parallel stream factorial implementation. There's a couple different versions of this. This is one of them. As you can see, this looks almost almost identical to the sequential stream version, with the difference that we put the dot parallel operator here, or operation here, which informs parallel streams to make this a parallel stream. So as you can see, boom, we get a big speed up in performance. You can see the difference between the sequential stream factorial, which took this long to run, and the one that uses parallel streams, which is substantially faster. And so it's, more than twice as fast for this particular run of the test. Okay, so that's just kind of illustrating how absolutely trivial it is to convert something from a sequential stream to a parallel stream. And now you're substantially faster than the for loop version we wrote earlier. Here's another version of the parallel stream implementation. It just uses the 3-parameter version of reduce, whereas this approach used the 2-parameter version of reduce. For the purposes here, they're essentially identical, and the performance isn't that much different. Now let's move into a couple of the reactive programming implementations. And they also look very similar in this case to what we saw with parallel streams. And that's because over time, people have baked in parallel processing as a first-class type in the reactive type system that you get, or the reactive operation system you get with both RxJava and with Project Reactor. So you can see here for the RxJava version, we use something called a flowable to make a stream of values from 1 to n. We turn that into a parallel stream or a parallel flowable just by using the dot parallel operator. Very simple. And then this looks almost identical to what parallel streams did. The difference again is because the reactive versions are fundamentally asynchronous. If we want to get a result back as opposed to a flowable to a result back, or a single to a result back, we're going to have to use a blocking operation like blocking single, which just makes sure it returns the value. The parallel Flux version is also very similar. It looks almost identical, it just uses a flux instead of using a flowable. And it uses a method called block instead of using block single. But otherwise, it's very much the same. So there's a parallel flux that goes along with flux. And you can see here that it has much the same structure as we did with RxJava. Now, as we get further into the course, we'll see that there's differences, more subtle differences and more dramatic differences between RxJava and Project Reactor. But for the purposes of this example, they're very, very, very similar. So that's an example, just kind of a Rosetta Stone showing how to write a bunch of different implementations of a relatively simple algorithm. But notice how you get tremendous performance boost by choosing the versions of the implementation that can leverage the various reactive and or functional parallelism mechanisms more readily. And I think nowhere is that clearer than looking at the difference between sequential factorial, which executes at this performance, versus the parallel versions. And just because they're somewhat more sophisticated in their use of streams or RxJava or Project Reactor, we can get a big boost in performance without much change, if any, minor, minuscule changes to our actual code. So that demonstrates, once again, the benefits that come from using a higher level frameworks, rather than writing the code using what's known as the accumulator anti-pattern, which is the way that people historically have written sequential algorithms like this.